This
My name is
conference will now be recorded.
Hello, my name is Rakesh Imnani. I work at Facebook. Today I'm going to be co-presenting with Gilad Wind from Mellanox. In our presentation, we're going to take an overview of some of the interesting challenges we are faced with multi-host NIC deployment in our data center and how the next generation of multi-host NICs is addressing them. As some of you know, we have Yosemite server architecture where multiple servers plug into the same chassis. This enables each one of these servers to take advantage of the shared resources, making it extremely resource efficient, which in turn enables higher compute densities for our deployment. In our presentation, we're going to be focused completely on one shared part, which is the NIC. If you take a look at the NIC, this NIC is shared between the 4 hosts. That's why it's called multi-host NIC. Each one of the hosts connects to the NIC with PCIe by 2 link. The NIC in turn connects to the switch with a single cable. So one NIC instead of 4 NICs, one cable instead of 4 cables. What does it mean to deploy this NIC or this architecture at scale? Each one of the servers in the Yosemite chassis is supposed to be an independent entity, which means each one of these servers could be running a different application or a different service, which in turn means the shared NIC gets exposed to 4 different traffic patterns at the same time. And this is exactly where some of our challenges come into picture. Now, if you take a network view of this architecture, there's an inherent network asymmetry. The 50 gig link from the switch to the NIC can bring in traffic for each one of the hosts at 50 gig, but each one of the hosts cannot drain from the NIC at more than 12.5 gig. So there is going to be some amount of buffering that's going to have to happen in the NIC. Given that, you can easily visualize a scenario where if there is a long enough network bust, it's going to fill up the receive buffer, and then some of the packets would have to get dropped. Now, if you take a look at it from an application perspective or a service perspective, what this looks like is if one of the service is bursty or getting a lot of traffic, this could lead to the packet loss for another service. This is in total violation of all these 4 servers being independent entities. So we got 2 problems. We got a problem with the host isolation, which means one host behavior could actually impact the other host behavior. And we have problem with the host fairness. That means one of the host traffic can actually come to dominate the buffer. Now, one of the ways we can try to prevent these packet drops is by implementing a pause, which means if the buffer gets full, it issues a pause, and all of the subsequent packet buffering happens in top of the rack switch. This helps you augment the switch buffer, augment the NIC buffer by adding a switch buffer to it. Does that solve the problem in all the cases? Definitely not. It only solves the problem when the burst is just large enough that the switch port buffer can absorb it. But you can easily visualize another scenario in which the application is so bursty that it fills up the NIC buffer, and then it fills up the switch buffer, so the subsequent packets for another application again get dropped. So our problem with the host isolation remains. In fact, if you look at the top of the rack switch, there's always some sort of a QS implemented. So here I'm showing example of 3 priorities. P0 strict priority and P2 is the lowest priority. Imagine a situation in which one of the apps, let's say app 1 is on P0 priority and the other apps, app 2 and app 4 on P2 priority. Now, if app 1 is extremely bursty, it's gonna fill up the NIC buffer, and then it's gonna constantly pause traffic coming down from the rack switch, thereby disabling the P2 traffic from getting to its app. And whenever this pause expires, it's the P0 that actually gets the priority to get down to app 1. And there are certain cases in which app 2 and app 4 could completely end up being devoid of their network traffic, and this causes a service disruption. So this, again, we have the fairness issue in top of the rack switch. So this causes interesting, challenging sets of problems that you need to solve. For example, maybe you cannot place a very bursty service with a latency sensitive service, but then the nature of the services is always changing. So it's kind of hard to put those kind of constraints on it. The overall problem statement is, if you are using the current crop of multi-host NICs, and if you cannot absolutely make sure that each one of the hosts cannot take more than 12.5 gig, then you need to craft a solution for this. And the solution could be, it's a system level problem. It has to be a system level solution. It could get many different forms. You could implement some sort of a shaping. You can implement DCTCP for congestion avoidance. You can try to avoid creating a microburst to begin with. The exact solution would depend on the context of the problem and the environment in which it needs to be implemented. Now, Elad is gonna explain more how the next generation NIC tries to overcome this problem. Elad, all yours.
Thanks, Rakesh. These are great examples. I'll try to summarize the challenges you raised in this coming slide and look at it from the NIC point of view and the complexities that the NIC sees. So with a shared NIC, none of the hosts is aware that the NIC is being shared, and therefore they all expect full isolation. So traffic isolation, data protection, these are all things to look for. And while this is a NIC, there is a heavy layer 2 switch logic. When the packets come from the wire, they are being switched into the right host, and therefore the NIC has to implement the heuristics and buffer and port logic, same as the switch does. And hence the split personality of being a multi-host NIC and a switch. To top that, the switch stitches together two fabrics, so Ethernet fabric and PCIe, which are very different. PCIe is credit system, and it has to be honored. So packets are not pushed; they're rather pulled, and these are things to look for. Lastly, is the built-in congestion that is inherent by the design, by the asymmetry of the design. As Rakesh mentioned, we have 100 gig traffic coming potentially to a single host, which will saturate at around 25 gig on its PCIe bus side. And if we're not going to do anything to avoid that, then that's going to be, the buffer will blow up really fast and the traffic will be disrupted. So that's another point that the multi-host NIC is challenged with, and we'll see how modern design can solve all of that. When you look into how the NIC architecture looks like, then we obviously think, well, there might be a huge buffer here in order to absorb all these effects and to make sure that we are able to compensate with a lot of buffers for the congestion that happens. But in reality, NICs don't have the big buffers that the switches do, and we implement a smart, flexible shared buffer in order to provide this fine granularity of quality of service of congestion avoidance, and to hit the goals that we set, which is traffic fairness, traffic isolation, and of course all that time line rate performance. So we're looking at a programmable packet steering, which can classify packets according to any field in the packet header. So not only the host and the port number, but also it can look into the priority that the packets are colored with, and we can try and bisect that traffic into according to different VLANs or according to different source addresses, and put them in dedicated egress pools. So the steering will put we push on the packets into output queues. Output queues is another switch mechanism been used for a while, and we implemented that in order to administer the queues, administer the buffer allocations, and wait for the scheduler to come and pick up the packets and send them on to the destination. So the mysterious count happens inside the scheduler. This is where the packets are being pulled out of the queues according to the to the order and the occupancy of them. Packets can be dropped altogether and not hit the wire, implementing W-read mechanism, or packets can also be marked, ECN marking, and provide the congestion notification to the end device, and the network will ultimately throttle down. So scheduler is a place where we'll implement flow control and congestion control into the device. And with this kind of a smart multi-host buffer, I think we're up for the game. When we took the ConnectX 6DX multi-host NIC from Mellanox, we put it on a multi-host server, 4 hosts, and the traffic that we pushed to it came through a switch from multiple servers, all of them with 100 gig NICs, and each running multiple hundreds of VMs to simulate realistic and bursty traffic, which will oversaturate. Well, the idea is to oversaturate the aggressor servers, the ones marked in red, servers 2, 3, and 4, and leave server number 1 to be the victim. The victim is supposed to receive a 5 gigabit per second flow, constant flow, and what we want to see is indeed that this victim will not be impacted with any of the phenomena described before. And let's see how that worked. So we collected here the bandwidth, the received bandwidth of every host in the system. And we can go and inspect together with some other metrics, the packet drops, retransmissions, how we did. The amazing result is that there is no victim. So the performance we got on the victim was 5 gig constant traffic, and there was no performance loss. There was no impact coming from the aggressor traffic, and we saw almost 0 retransmissions on the host. So with that, sorry, excuse me, we can declare isolation. What we also see is that the aggressors, they hit line rate. So for them, line rate, given that the PCIe bus is by 4 Gen 3, is around 27 gigabit, and we got to the realistic max of that, and it's fairly divided between them. And with that, I think that we can also show that we hit line rate performance with multi-host system. Lastly is the BMC. So the BMC is the little controller CPU that runs the multi-host sled, that provides the management and control for the whole platform. It also demands bandwidth, and we're able to maintain that and see no degradation in that bandwidth going into the management port. With that, let's conclude our session and call out the actions that we have. First is use multi-host servers in your environment to increase infrastructure efficiency. When you do that, you have to plan really well the congestion control across the whole fabric, applying flow control and everything that we discussed. You may want to leverage a smart multi-host NIC to meet all the quality of service needs, and you definitely need to plan to adopt a telemetry scheme for microburst detection. Thank you very much. I hope you enjoyed it.
Hey guys, this is Rakesh from Facebook. One of the questions we have from the meet is, does the NIC implement application level queues in the shared buffer? Elad, correct me if I'm wrong, but in the previous generation of the NICs, the RX buffer preceded any kind of classification. So the problem we were facing was the traffic was coming in at 50 gig speed, and it was overwhelming the RX buffer before it could be classified on a per host basis or for an application basis, thereby causing head of the line blocking. And this has been remediated in the new generation of NICs, but this is the kind of feedback mechanism we had going to our vendors that helped them come up with the new architecture. Does that answer the question, I hope?
Hi, Navneet. This is Elad from NVIDIA Networking, Mellanox. I would add to Rakesh's answer that the modern multi-host NICs, they implement a classifier mechanism which can use the 5 tuples or other header fields in the packet. And in this sense, you're able to provide a level of quality of service. There are different applications or different sources and streams, the way that you're able to define them in packet headers. It can be a layer 2, layer 3 packet header or any modified field. I hope this answers your question. Let's go to the next question. So Hemal Shah from Broadcom has asked, how does telemetry scheme help microburst detection? If we can elaborate. So certainly, Hemal, thank you for joining our session. A telemetry scheme would allow us to have a inner depth view per host or per queue, and even with finer granularity, especially when you're able to view that in a small scale granularity of time. With that, we're able to know whether an event is a microburst event or is it a congestion which is built into the network. We would want to resolve any obvious blockings that are by design in the network and focused on the microburst event. So it's very critical that the devices we're planning for will have the ability to finally cut what are bursts that are caused as microbursts in events that the applications have contributed to. And this will require further investigation with the telemetry data that we are able to collect from the NIC. I hope that answers your questions, Hemal. Let's see if there are other questions.
Hey, Elad, I don't see any more questions, so I think it's a wrap.
Mm-hmm.
Yep. Thanks, everybody, for joining our session. Have a great day. Bye.
Thank you, everyone. Bye-bye. Thank you, Rakesh.